Okay, so hello everyone, and welcome to my talk where I will discuss the reconstruction of meteoroid trajectories using a forward-scattering setup. So this is part of my PhD thesis that I'm doing under the supervision of Hervé, Lamy. So, I mean, you're quite familiar now. It's been the third time, so I will spare you the details. This is a BRAMS network, so it's a forward-scatter setup, which means that the transmitter is not located at the same place as the receivers. I would just like to emphasize what's important for our purpose of trajectory construction, which is that all of the receivers do not give any range or directional information. There is only one station, which is this red circle that you see, which has an interferometer that allows to get information about the direction of the incoming signal. For the others, we have not this information, which means that the problem is quite complicated. The only information we have is that our receivers detect signal and they are all GPS synchronized. So knowing that, how can we get the trajectory? Well, the idea is that here we are interested in a forward scatter reflection, which has the property of being specular. Specular meaning that for each receiver, the total distance traveled by the wave from the transmitter to the meteor trail and back to the receiver will be minimum. As a result, if you take two receivers, you will actually have a time delay between the two because the specular point will not be at the same position. So now to characterize this problem, we introduce 6 unknowns, 3 for the position of a reference specular point, and 3 for the velocity. So what we assume here is that we have a constant speed motion in first approximation, and since we have 6 unknowns, we'd like at least 6 equations, and so we need at least 6 signals from 6 receivers. This is basically what I call method 1. We take a certain number of radio signals at our different receivers. We extract the time delays because we know that our signals are GPS synchronized. And then we have to solve a quite complex problem, which is an inverse problem, where we have to retrieve our trajectory from the time delays. So this problem actually uses a target objective that we need to minimize. And basically what you see in this target objective is that we try to minimize the difference between our model and our experimental values. So we have a model which to each trajectory associates the theoretical time delay that we should observe on the ground. And so we subtract this quantity to our experimental time delays, and basically the best trajectory we can find is the one which minimizes this quantity. Then this gives us, through an optimization algorithm, our trajectory with our 6 unknowns. So this is method 1, no interferometric data, while method 2 basically minimizes this this awful target objective, where you have no 3 terms. The first one is the same as before, so it tries to minimize the time delays, and the other 2 basically use the information we have now at our interferometer, which gives information both about the elevation angle of the incoming signal and of the azimuth angle. And again, we put that into a solver, and that gives us our trajectory. So this is what I implemented. But first, before using actual signal, what I did was to generate a certain number of synthetic trajectories. This is a number of them. Here I put 11 of them. And what I did was to use my model to try to get what are the theoretical time delays. Then I extracted those time delays and I fed them into my in solver and tried to see if I managed to recover the trajectory I initially generated. This is what we obtained. So you can see on the right the errors we obtained on the reconstruction, and that basically shows that in terms of inclination, position, and velocity, we are really good. So that means that our optimization algorithm works and that we can use it for reconstruction. But in practice, we will never have access to the theoretical time delays. In practice, we have radio signals, and so we'll have some uncertainties. So we need to characterize that. How much that will impact the reconstruction, knowing that we have no perfect knowledge of the time delays. So to do so, I ran an uncertainty quantification campaign, which is based on Monte Carlo sampling. So basically, I introduced the reference frame we are using. We are centered on our transmitter. The XY plane is the horizontal one. And here are the results. So what you see here basically is an analysis of what is the output uncertainty on the y-axis as a function of the input uncertainties. What we see is that in terms of the horizontal plane here, it's actually quite good because we can have uncertainties of up to 10 milliseconds and still get a trajectory which is which has an inclination with an uncertainty of less than 1 degree. However, and this is where everything becomes very difficult, in the vertical direction, actually, it's much worse. So you need to have very good data because even if you have 5 milliseconds input uncertainty, and we will see that this is typically what we have, well, we already have errors on the output angles of about 10 degrees, which is, of course, not acceptable for a trajectory reconstruction. I'm not even talking about the position here, where you see that 5 milliseconds, well, leads to more than tens of kilometers of output uncertainty. With method 2, however, when we introduce the interferometric data, the problem becomes much easier. In that case, actually, you see that now the scale is different. Now we have errors, even in the vertical directions, which are of the order of 1 degree, which is much more acceptable. The position is already is also much better, and the velocity now is also very good. So the takeaway message of this is that method 1, so using time delays only, is a very ill-conditioned problem, and this is just intrinsically what happens. However, when we use interferometric data, that completely alleviates this ill conditioning. That shows basically the importance of having an interferometer in such a forward scatter setup. So I said that when we are using radio signals from which we can extract our time delays, I will quickly present what we do in terms of post-processing. So basically, we acquire our signal. You see a typical signal in the time domain, and then you see some peaks, and this could actually be a meteor. But to check if it's actually the case, we use what Antonio and Hervé already presented, which is the spectrogram. And you see that if you identify the signal in the spectrogram, you indeed see a meteoroid. And so in that case, we can try to zoom on this peak to try to extract a certain timing. I also show the direct signal, which is quite annoying because it brings no information, so we need to subtract it. This is the zoom on the meteor echo that you see in this green box. So you now see the typical rise of the signal, but we still need to further process this data. So as I said, what we do is to subtract the direct signal and then bandpass filter it, and then you obtain this kind of curves where you see now clearly the meteor rise and the exponential decay, which is typical of a small meteor. You see that there are actually 3 curves. I apply some smoothing in order to get rid of the oscillations of the signal, which still remain. And in that specific signal, we have to identify a precise timing definition. And it's actually quite tricky because we need a good timing definition of the meteor appearance in order to compute our time delays. But depending on actually what filter you use, depending on what smoothing you apply, depending on if you use the half-rise time or the peak time, it will give different time delays, and that can lead to very big uncertainties. So this is a summary of the post-processing we are using. So basically, subtracting direct signal, bandpass filtering it, apply some smoothing, identify one way or the other a timing on this signal, and then compute the time delays before feeding them into the trajectory solver. Now I will present the results we obtained with our radio signals, and to do so, I compare them with optical data coming from the CAMS network. So here's an example of a trajectory reconstruction obtained with method 1. So you see Belgium is here, and you see the target trajectory So the target trajectory, sorry, in red is actually the optical one, while the purple one is the one reconstructed through radio signals. And you see here the errors that you obtain. So you see that in terms of position, as expected, we are quite off with our radio reconstruction. But in terms of velocity and inclination, it's actually already satisfying. With method 2, as expected, everything becomes much better thanks to the interferometer. Well, now we managed to have an almost perfect superposition. You see the errors are very small. So this is a typical example of a trajectory construction. I show here next another example, because here we are above Belgium. Here we are just east of Belgium in Germany. You see typically the same behavior. So in terms of position, we are still far off with the method 1, using time delays only. But again, the velocity and inclination are quite well retrieved. And with method 2, again, the match is much better. So that, again, shows that method 1 is satisfying if you want to get information about the radiant and the velocity. You have errors of less than 2 degrees, and in terms of velocity of less than 5%. But if you want information about the actual location of your meteoroid, then you need the interferometer. This is the summary. And in terms of perspective, we still need to further calibrate the interferometer in order to get better data. And I'm currently investigating another method, which is called pre-T0 speed determination method, which uses the phase of the signal before the specular points. And in the future, we would like also to introduce some deceleration models to check if we get better reconstructions. So thank you very much for listening.